Hello everybody, I'm Bolei. Welcome to the Interpretable Machine Learning tutorial. Today I will talk about the interpretability of deep generative model. So the title is Exploring and Exploiting the Interpretable Semantics in GANs. So you know that there are a lot of previous work on the interpretability of deep neural network trained for classification, but there is much less work on interpreting the generative model, which already achieved very amazing image synthesized results. So I want to explore why those deep generative model can synthesize such photorealistic images. So let's first take a look at the progress for the GANs synthesizing images. So in 2014, GANs introduced by Ian Goodfellow. So the image quality is not that good. You can see those images are just 32 by 32 blobs. You can barely see anything inside. But over the years, there is a great progress made to synthesize high-quality images. So you can see from this DC-GAN to PG-GAN to big-GAN, we can synthesize such a photorealistic images. On the other hand, for the face and the different generic objects, the PG-GAN and the style-GAN and big-GAN can synthesize images with high variations, such as different genders and hairstyles and skin colors and even different ages, such as children's and adult. So given such amazing GANs synthesizing photorealistic images, we may wonder what have been learned inside the internal representations. So that's why we want interpret to understand the internal representations. Hopefully they can bring some side applications that we can manipulate the output images. So this is our motivation. So probably everyone familiar with this generative adversarial training process. So basically to train the GAN models, there is this training mechanism that there is this generator which will take a random noise, then it will generate synthesized images. Then there is another network called the discriminator. So discriminator will classify the synthesized image or real image into the labels. So basically the purpose of the generator is to generate synthesized images to fool the discriminator. The role of the discriminator is to differentiate whether the input is a real image or fake image. Through such adversarial training, so the generator can learn the general distributions of the input data so they can synthesize realistic images. So here today's lecture will not talk about training pipelines. We will focus mainly on this well-trained generator. So this generator is just a convolutional network. So after training, it can synthesize realistic images. So we want to interpret, understand the internal representations and why this generator can synthesize such nice images. So the tutorial outline, I will divide my talk into two parts. The first part is exploring the semantics in the latent space. How can we propose different approaches, the supervised approaches and unsupervised approaches, to identify the semantics that emerge inside the internal representations and or the latent space of the generators. Second part, I will talk about the inversion of real image, such as we have a well-trained generator, so we can only get synthesized images, but giving some real images, how can we map those real images back into the latent space? So we have to use some inversion techniques. Okay, so let's talk about the first part. After training, we have this generator. So the generator is a deep generative representation. So basically, this generator is a convolutional neural network. So it's doing this up convolution to synthesize the image. So after we sample some random vectors, so let's say this vector has 512 dimensions. So we sample from some random distributions, such as a Gaussian distribution. Then we can throw into the generator. So the generator will synthesize image corresponding to this input random vector. If we change this random vector, the output will also change. So we change another one, output will change. So given this representation, so there are two latent representations. One kind of latent representation is this latent unit. So you see this convolution filters. So we try to understand those latent units, what knowledge have been captured by the internal convolution filters. So here we call those filters as the latent units. Another part is this very beginning latent space. So latent space is where we sample the random vectors. So this random vector is a driven force for the image synthesized. So we can identify some variation factors in this latent space that we can control the semantics in the output space. Let's first take a look at this GAN dissection. So GAN dissection is a work published at iClear last year, done by David Bolei. So GAN dissection is an extension of our previous work on network dissection. So it's a framework to interpret and label the internal units inside this generator. So basically, this framework will take this generated images, will apply a semantic segmentation network to generate a semantic mask. Then after there is this unit feature map. You will upsample this feature map and computes the correspondence between this feature activation and the semantic mask. Therefore, we can associate a label for each one of the internal units. So after we apply the GAN dissection to this generator, we can label those units with high semantics, such as we have this unit labeled as door and the unit as labeled grass and clouds, so different semantics. So after we have this unit semantics, then we can control this unit by turning on and turning off those units to manipulate output image. So here I show you small demos on this interactive acting. So basically, user can just brush on the synthesized image. Then we can control the turning on and turning off the internal units. Then we can to remove and add some image contents inside this image. Such as we can brush the sky and also remove this grass and turning off the grass units, and also change the building styles. After we identify the semantics of the internal units, then we move to the latent space. So given this latent space, so we want to know how this latent space controls the semantics. Because basically this latent space is a driven force behind the synthesized image. Given different latent space, the images will be different. So here I first showing you a random walk in the latent space. So basically, we first randomly sample, get some samples, and each time we will add small perturbations in the sampled vectors, then it will generate some variations. So therefore, we can do this random walk in the latent space. So from this visualization, you can see that in this latent space, there are a lot of different variation factors to describe the scenes. We change the latent vectors, and you can see the layouts of the beds and the color of the sheets, and even the windows, and one bedroom changing into two beds. So a lot of different concepts have been encoded inside the latent space. Therefore, if we can identify those factors, then we can control the output images. Given a scene, there are actually different level of descriptors. For example, given this image, we can have this semantic descriptor at the category and attribute level, such as this is a bedroom. Then for the attributes, it's nature, lightnings, and woods, foliage inside the image. We also can have this layout descriptor for this image to describe this 3D structure of the scenes. Also, we can have this content descriptors, such as applying the semantic segmentation to this image. Then we can get every object inside the image, such as ceiling, window, bed, floor. So there are multiple levels of scene descriptors for the scene images, which create the difficulties to understand the models. So recently, we proposed a technique called high GAN to identify the semantic hierarchies that emerge in deep generative representations. So basically, giving this neural network trained for scene synthesized, so we have this generator giving random vectors to synthesize the image. Then we can extract a lot of semantics. So right now we want associate this predicted semantics back into the latent space to identify those causal effects relations. So if we can identify those causal effect relations, then we can successfully control the semantics. So how this framework works? So basically, we want to align the latent space with the attribute space. So right now we have this latent space. So it's latent vectors sampled from some Gaussian distribution. So after we can generate a lot of samples and throw into the generator, then we can get a synthesized image space. So the synthesized image space will have different synthesized samples with different semantics. So what we can do is that we can apply some off-the-shelf classifiers. So let's say this classifier is this indoor lightning classifier. So we can divide the synthesized image into this images with indoor lightning and without indoor lightning. So we can have this attribute space. So right now, after we have the attribute space labels, then we can treat those predicted labels as a ground truth labels for each random vectors in the latent space. Then we can simply train an attribute classifier in the latent space, then we can classify their semantics. It turns out just using a linear classifier, we can achieve 90% binary classification accuracy. So to classify the latent space, latent vectors into indoor lightning and later lightning. So after we train this classifier in latent space, so we have boundaries in the latent space. So after we have these boundaries, what we can do is just push the latent codes through the boundaries. So let's say previously we have 2 samples. So in the latent space, then we just push them towards the boundaries to increase their indoor lightnings. So let's say at the beginning, those 2 images, synthesized images are like this. So there is no indoor lightning there. Then we gradually push them across the boundaries. So magically, you see the whole rows are lighted up in a very realistic way. Not only the lamp is turned on, but the general lighting conditions of the rows also change. So it's a very realistic manipulations. So here I will show you some live demos on turning off the lights. So I will play a magic. So you notice there is a lamp in the scenes. So I want to change turn off the lamp. Gradually you see the lamp in the scenes are turned up and all the lighting conditions have been realistically added. Not only we can identify this indoor lightning boundaries, by applying different off-the-shelf classifiers, we can identify different semantic boundaries such as wooden and non-wooden, cloudy and non-cloudy. So after we have these semantics boundaries in the latent space, so we can do a lot of interesting manipulations, such as here, we want aging the scenes. So right now we have this modern bedroom, so we want to imagine the scenes after 50 years, how they look like. So we can age in the scenes. So they look how they look like after 50 years. So it's more like a horror movies. So you don't want to stay in such a bad rooms. So here's another one. So sometimes you took some photos, but the weather condition not that good. So there is no clouds in the sky. So we can apply our techniques to include more cloud in the scenes. So here we push the code toward the cloudy boundaries. So gradually you can see there is clouds emerging in the sky. So especially for the second samples, you can see even there is the sunset colors and shadows on the buildings. So it's a very beautiful manipulation. Also here you see those are the church buildings. So there is no green space. Then we want to add more green space inside. Then we push the latent codes towards the green space boundaries. So magically the green space emerge inside along with the buildings. Very interesting for the first example. You can see this generator is smart enough to put a sidewalk on the grass so people can walk. So it's really showing that the generator, the GANs, really know the semantics and also the compilation of visual concepts when they learn to synthesize the things. So this is a very interesting insight from the understanding of this generative models. Previous GAN models, so such as the DC-GAN and the PG-GAN. So they only have this stochasticity at the beginning. So here the stochacities means where the randomness come from. So right now we only have this random vector at the beginning and throw into the generators and synthesize the image. So the stochasticity only happens at the beginning. But later on, researchers propose much better model, the style GAN models. So for the style GAN models, the biggest innovation is that they change this beginning stochasticity to layer-wise stochasticity. So basically, at the beginning of the style GAN, they just input a constant vector. Then at each layer, they have stochasticity vectors introduced. So each layers will have a stochasticity. So that will largely enrich the encoding capability of the latent space. This also gives us the opportunity to interpret the latent semantics that's across different layers. So this style GAN greatly improved the synthesized qualities. Also, it gave us the opportunity to control the semantics in different ways. So we have this layer-wise stochastic vectors, and we can apply our high GAN framework to interpret those stochastic vectors. So after this layer-wise analysis, we notice there is a very interesting semantic hierarchy emerge inside the layers of the generators. So we apply high GANs to each layer hidden vectors, then analyze their importance to different concepts. So here I'm showing you a plot. The horizontal axis is the layer depth. The vertical axis is the importance of that layer to some concept, from this layout to objects to attributes to color scheme. So you can see those layers at the beginning, they control the layout. They gradually decrease. Then the layer in the middle, they control the object and attributes. The layers that closest to the output image, they control the color scheme. So we notice there is such a semantic hierarchies emerge inside this deep generative models. Then we can control the different layers to control the manipulation of different concepts. So here I will show you showing you some of the semantic manipulations. So here we control the layout as a layer 0 and the layer 1. So basically, after we have the samples, we can just change the latent codes as a layer 0 and the layer 1. Then we can rotate the layout of the scenes. So this result is very interesting because when we train this network, all the training data is this unpaired data. Those are just the bad rules collected from the web. We don't have the correspondence along the images. The GAN somehow just know the semantic correspondence. So they know such as 3D information or some 2.5D information about the scenes. Then if we can identify this layout factors, then we can just rotate this image in the image space. So this is a very impressive result. So here we also change the categories. So here basically the category is determined by the object inside. For example, for the same rule, if you put furniture such as this lamp, cabinet, bed inside, then this rule will become a bad rule. But if you put a sofa, TV, and table inside, then it will become a living room. So therefore, we can control the categories by controlling the object inside the scenes. So after we learn those boundaries for the categories, then we can change the category of the input image. So here are the examples when we push the samples from one category to another category. So you see at the beginning, this is a bad rule, then after that it becomes a dialing rule. But the general lighting conditions as well as the layouts remain the same. It's just only those objects are changed. So it's more like we move out different furnitures and move in the corresponding furnitures, and this category labels can be changed. So we do this manipulation as layers 3 to 6. So here is another one. We can also change this bedroom into living room by varying the latent codes at the layers 3 to 6. So here you see after we push in the codes, the bed actually change into the sofa because they are very close to each other. And also interestingly, you see this lamp. The lamps remain there because there is a lamp in bedroom, also lamp in the living room. So this concept will stay there after we push the latent code. So it's really showing you that the generator really knows the semantic, high-level semantics about the living room and the bedrooms if they can train to synthesize such realistic images. So let's take a look at another generative representation. So here we have a generator that trained to synthesize face. So we giving this random vectors, this generator will synthesize a realistic face. But one issue with this face synthesized generator is that we cannot change the semantics. So there is no way that we can change the semantics, such as we want a different angle for the person, and we want a different age for this output image. So therefore, we can do a random walk interpolation in the latent space of the face synthesized GANs. So you can see that in this latent space of face synthesized model, there are also a lot of semantics inside, coded inside, such as the gender, the hairstyles, the color, skins, and a lot of variation factors about the face already encoded inside the latent space. So which give us the insight if we can label or identify those hidden semantics, then we can control the output images. So therefore, follow this insights, we propose a technique at CVPR this year called the InterfaceGAN. So it's a technique to bridge the latent space to attribute space. So it's actually similar to the previous high GAN work. So basically we have this latent space. We can sample a lot of points and throw into the generator. Then we have this image space. Then we can apply some off-the-shelf classifier that gets us attributes. And for this particular example, this classify into different male and females. Then we can use this predict labels again as a ground truth label and train classifiers in the latent space. Then we have this boundary in the latent space. Then we can change the latent code. For examples, we want to change the semantics. Like for this persons, we want to make this guy look cooler, and we can improve the semantics by putting a glass here. Now for this young lady, they want to make me look younger, then we can change the age of this lady and make her look younger. For this, the pose is not that good, so make me front face. Then we can change the pose of the persons, and also for this to make me more man. So this is a weird requirement, but we also can satisfy this requirement by changing the gender. One very interesting phenomenon is that even the image qualities can be considered as some boundary in the latent space. Because sometimes when we generate the samples, the GANs will make some mistakes. Those are the 4 synthesized images. So you'll notice there are some artifacts inside the images. So after we identify this boundary controls the image quality, then we can push those images, then correct the artifacts made by the generator, made by the GAN. So here I will show you a demo. So the demo video, like we can continuously change the manipulation, change the attributes of the synthesized face. So here we show you the results changing the pose of the person. So you can see the identity of the person preserved, but the pose changed. Here we can change the expression. So they are smiling. So it's a very realistic expression manipulation result. Here we also can change the age, make them look older. So you see this teeth. So it's a very realistic manipulation. So here we also can change the gender of the persons. And the male will push into the female. But for some of the attributes, it's not so well defined. So here is the eyes glasses. You just pull the glasses. So the glasses is more like automatically grow out from this image content. So here is the artifact correction. Okay. So at the same time, there are many other works also exploring the latent space of the GANs. For example, this work done by Ali, Lucy, Philip from MIT. So they analyze the stability of the generative adversarial network. So basically, they also propose some techniques to identify the circle dimensions in the latent space. Then they can like zoom in and zoom out the synthesized image, and also they can achieve the rotation for this image synthesized by the big GAN. So here is also another work from Philip's group. So they propose a framework called the GANalyze for changing the image memoriability. So basically, they have this pre-trained generator. So they use a big GAN. Then there is this transformer. Then there is this accessor. So accessor is a network, is an off-the-shelf pre-trained network that can predict the memoriability of the images. So they can use accessors to train these transformers. Then they can change the memoriabilities of the synthesized images, such as for the stock. They can improve their memorability. So when we zoom in, then these images become more memorable. And also for this peppers, when this green peppers turn into this red pepper, this image become more memorable. So that corresponds to our cognitive definitions. So that's a very interesting work. So I encourage you to check this paper out. They published at ICCV last year. But the one issue with this previous approach, such as GAN dissection, InterfaceGAN, and this high GAN or GAN hierarchies done by us, and also this GAN analyzer, is that all those approaches need some sort of supervision, such as the semantic mask, and also this predictor, semantic predictor to generate the semantic space, and also this accessor. So they have to use this off-the-shelf supervised classifiers. Then we can use this classifier to identify the latent semantics. But a lot of the, some of the latent semantics, we may not have this classifier, pre-trained classifier. Then how can we identify the semantics in unsupervised learning way is still long-standing problem. So there are some previous work that try to attack this unsupervised attribute discovery. So one of the earliest work is this InfoGAN work. So in this InfoGAN, they propose some training regularization. So they introduce this training regularization to maximize the mutual information between the latent codes and also the synthesized image. So therefore, after they introduce these regularizers, the resulting latent dimensions will correspond to some semantics. So in their paper, they show that some of the latent dimension, they control the pose. Then some of the latent dimension control the elevations, lightening, and wide and narrow. Then we train on this color phase, and they also show some of the dimensions correspond to some semantics. But one issue with this InfoGAN is that nobody knows whether this InfoGAN works for those high-quality GANs, such as the PGGAN and the style GANs. As far as I know, there are no implementation of InfoGAN on style GAN or PGGANs. So also for those images, you can see they are quite small. Sometimes it's really hard to tell whether this InfoGAN works. But I guess it works in some of this toy dataset, but for those high-resolution images, it's still very challenging to identify and disentangle different attributes on each dimensions. So there are some recent, very recent work, probably just published, put on archive 1 or 2 months ago, such as this work from Andrew and Anting on unsupervised discovery of interpretable directions in GAN latent space. So they propose some techniques that they put some noise in the latent space, and they just generate the image, and this, they have this another module to predict this input noise. So that they can also learn some interpretable dimensions, such as some dimension controls the thickness, some dimension control the hair and the background. They also show that some dimension even control the background, so they can change the background or remove background for some images. So that's a very interesting application. So here is also another very recent work called the GAN space from Adobe Research. So they apply the principal component analysis on the latent activations of these generators. Then they can learn the most important component in this latent space. So after they have this PCA on the latent space, then they get the different components, and they can control these components to synthesize the images, to control the semantics in the images. So here I will show you a demo from the work. So you can see here they have different components, so they can just draw these components and then change different attributes of this car. This is a control for the face. So they also can they can control the head of the bird. So that's a very interesting result. So this also they show the background is also controlled by some disentangle vector. Okay, so let's continue. Also, recently we have work on learning the disentanglement of the attributes in the latent space. So the difference is that we just propose a closed form solution to disentangle the non-linear representations. So rather than analyzing a lot of samples, so we will release this submission very soon. So here I show you some results. So after we learn this disentangle dimensions, so some of the dimensions correspond to the pose, and we can change the pose. Like for the anime face, we can change the size of the mouse, and also for the body pose of this cat, and also the layout of the bedrooms. So it's a very interesting result to learn such unsupervised disentangle dimensions. But there are still a lot of existing issues for the unsupervised approaches. For example, how to evaluate the discovered interpretable dimensions. So many of the previous work I introduced, they just show some qualitative results. It's really difficult to measure how well this interpretable dimension works. So then this involves the second question, how to measure the disentanglement of the representations. So I think we have to propose some protocols to evaluate the interpretable dimensions, such as maybe we can just measure the alignment between the disentanglement with some supervised data. Then we can measure how disentangled this dimension is. The third issue is how to compare different methods, because different unsupervised learning approaches, they will learn different dimensions, and it's really hard to align the interpretable dimension discovered by different approach. So it's still unsolved problems. Okay, so let's move into the second part. I will introduce inversion of real images. Previously, I talked about that we can use a latent space to edit the synthesized image. So we can make a synthesized image look cooler and also change the age of the synthesized image to make this photo look younger. But what we really want is to edit our own image. So here I show you my previous profile photo. So luckily, after I become a faculty, I get more here. But for this profile image as example, so I want to edit my own photo. So we have this issue for GAN inversion. Previously, this generator, we just get some samples and we can synthesize this image. But given this real image, if we want to get the latent codes, then we have to solve this GAN inversion problem to invert the real face to the latent code. So we have to solve this minimization problem. So given any latent codes, we want to minimize the distance to the real image x. So we want to solve this optimization, then we can get the Z star that can reconstruct my face. So here, let's take a look at this particular examples. So let's say use my previous profile image as input to optimize the latent codes. Then after we have the optimized latent codes, this star, then we put it into the generator and see what can be generated. So are you ready? So it generates some image like this. So I'm pretty sure it's not my face. So let's put them side by side. So you see this is actually pretty challenging task. I can change different random initialization and do this minimization task. So here is the typo should be minimization. So it turns out it really depends on the random initialization. So it depends on the random initialization, they just generate a different version. I mean, Western phase version of me. I guess that's also showing one of the BIOS in the generator, that they just train the generators on the Celebrate HQ. So Celebrate HQ is only contained celebrities in Hollywood. So there are not so many Asian celebrities in Hollywood. So I guess so they can only synthesize such Western phase. So to improve this inversion results, so we can take a look at this extended latent code. So as I introduced in previous slides, that's from DCGAN, PGGAN. There is only one single code at the very beginning. So, but for the style GAN, there are actually multiple latent codes at each layers. So that actually extends the dimension of all the latent codes. So right now for the style GAN, so there will be multiple latent codes at each layers. Then we can jointly optimize their latent codes to reconstruct this image. So this kind of work is actually from this image to style GAN. So this is ICCV paper. So embed the image into the style GAN models. So they propose this optimization to optimize multiple latent codes to reconstruct the image. So it's actually kind of works. So here is a target image. So on this middle is the inversion from the single codes. So here is the inversion from image to style GAN. So it's using multiple latent codes to reconstruct the image. So it can reconstruct the input image very realistically because they extend the dimension of the latent space from 512 to 14 times 512. So that actually greatly increases the dimension of the latent space. Therefore, this latent space can have stronger representation capabilities. Then we can just reconstruct this given image in a very realistic way. However, we notice there are some problems for this kind of reconstruction. So it seems this image to style GAN just overfits the given image. So here is an experiment we have done. So giving this style GAN generator, so this generator is actually only trained on human face. So only all the training data are human faces. So right now we just give some long face image to this generator, such as we have a cat image. Then this image to style GAN can actually reconstruct this cat face. Also, we can throw a bedroom image into this generator trained on human face. It can also reconstruct this bedroom to some degree. So which means this image to style GAN seems only borrow different low-level features to reconstruct the pixel values rather than understand the semantics. So here is another experiment to verify this overfitting issue, such as here after we have this reconstructed Bush previous president images, then we can apply our InterfaceGAN to manipulate the attributes. They turn out after we vary the inverted codes a little bit, such as add some space, small add glasses, the image quality is greatly decreased. So which means this latent codes in actually not in the original latent space of this generator. Then we cannot very nicely manipulate this inverted latent code to achieve realistic image editing results. So this is an issue. This is one issue we found out, that the resulting inverted codes may be out of the original latent dimension, such as right now we are solving this optimization problem. So here I just, for simplicity, I include multiple latent codes into the single notation Z. So we more optimize this, then this optimization is an unconstrained optimization. So then we have this image, then we optimize this, but the resulting inverted code may be just outside of the original latent space, latent domains, so which result in this out-of-domain inversion. So given this out-of-domain inverted code, we cannot manipulate this code in a very nice way. So what we can do? How can we improve this inverting process? So let's take a look at another issues that's introducing the encoder to the GANs generator. So one shortage for the GAN generator is that it lacks this inference ability, such as here, given this generator, we have the X. then there is no encoder. If we can have an encoder, then we don't need to solve this optimization problem. So there are a lot of recent work that try to add some encoder to the generator. So basically, if we can have this encoder and give any real image, so we can use this encoder to generate this latent code, then give this latent code to the generators, then we can reconstruct this image. So here I list some of the recent works, such as this Big by GAN. They propose some encoder to the GAN big GAN model. Also this ALA work, Adversarial Latent Autoencoder, published at the CVPR this year. They also introduce an encoder to the generator. Also, we have some recent work in domain inversion, also propose some encoder to generate the latent codes. One issue with this encoder-based reconstruction is that they cannot achieve a realistic reconstruction. For example, we have this input image, but it can reconstruct a very different object. Also for this ALA, given this Obama image, can reconstruct the identity totally changed. And for our recent work, although we can reconstruct image to some degree, but still the identity of this person changed. So which means it's very challenging to introduce an encoder to this GAN's adversarial training pipeline. But what we can do is that we can use this encoder as a constraint in this optimization. So previously we have this unconstrained inversion. Right now this Z just floating random variables. Then we optimize that. That will result in this out of domain codes. Then we have this work that includes the encoder into this optimization process. So we use this encoder as a constraint for the optimization. So besides this mean loss, we also introduce this encoder loss. So you see this encoder. So after we have this reconstructed image, we will put into this encoder again, and then minimize the distance to the code. So with this constraint of encoders, we can make sure the inverted codes lies inside the original latent space. Therefore, we can manipulate this reverted code to achieve the image editing application. So here is a comparison with the image to StyleGAN. So you see here is a reconstruction result. So the reconstruction result from image to StyleGAN and in our in-domain inversions approximately is the same. But for the manipulation results, so our result is much better than the image to StyleGAN's result. You see, you can change the age and add smile and also add glasses, while other attributes can be preserved. So that also shows that the inverted codes from this encoder constraint optimizations can keep this properties of the latent code, semantics of the latent code. So here I will show you a video demo to manipulate the real face images. Here we can change the pose of the person. So here we can add the glasses, change the gender, also change the age, change the expression, make them smile. We also can do some interpolation results. So giving the inverted code from two images, so we can change the intensity of the to do this interpolation. So here is the comparison with image to StyleGAN's inverted codes. So our interpolation result can achieve more smooth interpolation. Also here, we also can achieve some fun application, which we call semantic diffusion. So the semantic diffusion is that giving this target image. So we just take the image crop from this target image, then we put them into the context. So here we have 6 context images. Then just use a background as a context. Then we can optimize, apply our in-domain inversion, and then put the constraints inside this bounding box, only more optimized to keep this foreground the same, and let the background and let the context change according to this constraint of the foreground. So then the background can adapt it to the foreground to create such a semantic diffusion result. So you see this background is automatically adapted to the foreground. Then we can change different style of the same persons while keep their identity. Later, we also have some other works that apply the trained representation of GAN as an image prior for a lot of image processing applications, such as here for this colorization, for super resolution, reconstruction, image imprinting, and semantic manipulation. So this work is also published at CVPR this year. Finally, here I would like to acknowledge my research team at the CUHK, Yujun, Ceyuan, Jingjing, Jiapeng. So they have done incredible work to push this generative modeling work. So here we release all the code and the papers at this GenForce link. So there is this demo videos as well as well-polished codes. So you can check them out. Okay, so here is a summary. So interpretability of generative model is a rising topic because the generative models can synthesize more and more realistic images. So in their internal representations, they should know a lot of different level of semantics about the data distributions. So if we can identify those interpretable factors, then we can achieve a lot of side applications. This is the end of my tutorial lecture. So if you have any questions, please leave a comment below. I will try to respond them. Okay, hope you can enjoy other speakers' lectures. Bye-bye.